All right, in this section, we're going to talk about the graphs of the sine and the cosine functions. We'll begin by talking about what's called the period of a function. Now, every day due to the Earth's rotation, we see that the sun rises and then it sets. We see that every single day. And this behavior over the course of a year is periodic in that it is regular and it's predictable. Now, this is behavior that we've seen before in a circle, where a point moves around the circle, it completes a full rotation, and then it does it again. In fact, this is what we would say is called the period. A period of a function is the shortest interval over which a function completes one full cycle. Now, to get more specific, we would say that the period of a function f is the number p representing the interval such that f of the quantity x plus p is equal to f of x for any value of x. So if the output of f of the quantity x plus p is equal to the output of f of x, so they are equal, then whatever that p value is, that is what we call the period. Now, let me show you an example. We know that 60 degrees and 420 degrees are coterminal because they share the same terminal side. What that tells us is that their sine and cosine are equal, where the cosine of 420 degrees is equal to the cosine of 60 degrees, and the sine of 420 degrees is equal to the sine of 60 degrees. Now, that 420 degrees can be rewritten as the sum 60 degrees plus 360 degrees. 60 degrees plus 360 degrees. Notice that the 60 degrees is our x value. What x value am I talking about? I'm talking about the x value that was in this definition. And that leaves the 360 degrees as the p value. And that p-value is the period of that function. Now, it turns out that the period of the cosine and sine functions in general are 360 degrees, or if we are in radians, 2 pi radians. Now, what does this have to do with the graphing of the sine and the cosine function? Well, by knowing when these functions repeat, so every 360 degrees or every 2 pi radians, it means that we only have to graph one period of a function in order to then see it repeat, to see that pattern repeat and complete a graph. So by creating a visual representation of a periodic function in the form of a graph on an xy axis, we can analyze the properties of the function. So let's take a look at what that might look like on an xy axis. So let's talk about the graph of the sine function. Now, in order for something to be a function, we know that there is an input and there has to be an output. So if I want to graph the sine function on an xy axis, an x and a y axis, an input and an output, then I need to have an input, which for the sine function will be the angle, theta in this case, and an output, which in this case will be whatever the sine of theta is. By having an input and an output, that will give me an ordered pair, which is usually in the form x comma y, but for us it will be theta comma sine of theta. So let's start with an angle measure of 0, and in this case that's 0 radians because there is no degree marker above that 0. What is the sine of 0 radians? What is the sine of 0 radians? Now, if you don't have your unit circle memorized, I have gone ahead and put a unit circle here, and we can see that at 0 radians, my sine is 0. So that creates a first point, in this case, at the origin. Now let's talk about what is the sine of pi over 6. The sine of pi over 6, here's pi over 6, and the sine of pi over 6 is 1/2. So that creates the ordered pair pi over 6, comma 1/2. And I can keep going around the circle. I don't have to write the sine of pi over 2, for example, every single time. I can simply, hopefully, have this memorized and just write it down. So 5 pi over 6, I can see that the sine of 5 pi over 6 is 1/2. So I'm just going to write 1/2. And I'm going to then write the ordered pair. You might want to just pause the video and see if you can fill this out on your own without my help, and then come back. I will keep going, however. So for 7 pi over 6, the sine of that is -1/2. For 3 pi over 2, the output is -1. For 11 pi over 6, the output is -1/2. And I think for 2 pi, I am back around that circle, having done a full period. So 2 pi, comma 0. Now what I want to do is take all of these ordered pairs and I want to plot them on a traditional XY axis. So let's take a look on the next slide of what that might look like. So now we're ready to plot those points, and the table that we created in the last section is listed on the right, and we have a horizontal axis and we have a vertical axis. We have an input, we have an output. The input is going to be theta, and that is our angle, so that's marked on the horizontal axis. And on the vertical axis, our output is whatever the sine of theta happens to be. So we're going to plot those points, and the very first point that we see is the point 0, 0. So an angle measure of 0, an output, sine of 0 is also 0, places us at the origin. Pi over 6, 1/2. So I'm going to the right, pi over 6, I'm going to go up to 1/2. Pi over 2, 1, to the right, pi over 2, up to 1. And you sort of get the feel for this. And I hope that you're noticing that there appears to be a little bit of a pattern. We're going up, we're going down, and we're going to come back up. And finally, we're going to end up at 2 pi, 0. Now, we're going to connect those points with a smooth curve. And the reason we're going to do a smooth curve and not something that is, say, linear is because, of course, the unit circle is not linear. It has a curve to it. So it's going to look something like this. And because we've started at 0 and we've gone to 2 pi, then what we have just graphed is one period of the sine function. And this is always going to be the picture that you will see if you are graphing the sine function. Now, a couple of questions. You might notice that from 0 to pi, the sine values are positive. From 0 to pi, the sine values are positive. Why is this? And then, of course, from pi to 2 pi, the sine values are negative. So from 0 to pi, the sine values, the outputs are positive, and from pi to 2 pi, the sine values, the outputs are negative. Why is that? Well, that is because these values come from the unit circle. And from 0 to pi is quadrant 1 and quadrant 2. And we know that in quadrant 1 and quadrant 2, these sine values are positive. The sine values are positive. And then from pi to 2 pi, that's going to be quadrant 3 to quadrant 4. And that is where the sine values are negative. So it's all coming from that unit circle that we studied earlier. So if you forget what this picture looks like, you can always go back to that as a resource. So here is a nicer version of the sine function that I just drew. We see this one also starting at the origin and ending at 2 pi comma 0. Now, I said earlier that this was graphing one period of the sine function. If I was able to pick this picture up and stamp it to the right and stamp it to the left, then I would get something that just continues in that same pattern. And it would continue indefinitely. So that tells us something about the domain and the range. The domain of the sine function, it's just going to keep going. So this is going to be from negative infinity all the way to positive infinity. And the range of the sine function, let's see, what was the largest value we came up with and the smallest value? Because we were on that unit circle, and we know that even if we're not on a unit circle, those ratios are still going to give us outputs that are no larger than 1 and no smaller than -1, including both of those values. And so that's why you see the brackets on this one. Now let's take a look at the same thing, but with the cosine function. We do have a function, so again we have inputs and we have outputs. And our input is going to be theta, and our output is going to be the cosine of theta. And I'm still in radians. I could do this in degrees, but I'm trying to get you comfortable with radians. So the first question is, what is the cosine of 0 radians? And if you have the unit circle memorized, then you know that at 0 radians, you are at a cosine value of 1. And that creates the ordered pair 0, 1. Now I'll go ahead and put the unit circle on there again for you and just reiterate that when we were at 0 radians, then the cosine is in that first position was equal to 1. When I'm at pi over 3, the cosine value is 1/2. So the cosine of pi over 3 we know is equal to 1/2, and that creates the ordered pair pi over 3, comma 1/2. Now, one thing that you might be thinking to yourself is, when you go to graph that point, pi over 3, comma 1/2, if you haven't made your horizontal axis in theta increments of pi over 3, then how do you graph it? Well, remember, pi over 3 is just an exact input. You could plug into your calculator pi, which is approximately 3.14, and divide that by 3, so you'd get something a little bit larger than 1 that you could then use on your horizontal axis. But graphing these exactly is always the best route to go. So try to keep that in mind when you're graphing yourself. There's no reason why you can't make the increments on your input-output axis whatever you want them to be. Okay, so at pi over 2, I have an output of 0. So I'm just going to go ahead and write that down and put the ordered pair pi over 2, comma 0. And if I were you, I would pause this video and see if you're able to fill in the rest of these ordered pairs. So I'll just list these points. I've got pi, comma -1. At 4 pi over 3, it looks like I'm at -1/2. So 4 pi over 3, comma -1/2. 3 pi over 2, I'm at 0. So 3 pi over 2, comma 0. 5 pi over 3, I'm at 1/2, positive 1/2. 5 pi over 3, comma 1/2. And finally back to 2 pi, and I am at 1. Back to where I started. So now what I want to do is pick up these points, plot them, and create a cosine function. So here are those inputs and outputs, those points. And just like we did with the sine curve, let's go ahead and plot those. So 0, 1 is going to be up on that vertical axis. Pi over 3, 1/2. Pi over 2, 0. 2 pi over 3, -1/2. You're seeing that pattern, a different pattern, but you're seeing something that looks familiar. 4 pi over 3, -1/2. 3 pi over 2, 0. 5 pi over 3, 1/2. And finally 2 pi, 1. All right, so I'm going to connect with a smooth curve, and it's going to look something like this. Now, what I hope that you're thinking to yourself is, okay, well, this isn't exactly the same positioning, but the shape does feel like it's the same, doesn't it? We see that, you know, it goes up the top, and then it has to come down, crossing the horizontal axis, and then it comes all the way down. So there are some similarities between the sine and cosine function. This one's a little bit different though, because from 0 to pi over 2, let me just go ahead and circle that. From 0 to pi over 2, the values are positive. And then also from 3 pi over 2 to 2 pi, the values are positive. And then, of course, we see that they're negative from pi over 2 to 3 pi over 2. That's where they're negative. And why is that happening? Well, the answer is the same as it was for the sine function. From 0 to pi over 2, we are in quadrant 1. And in quadrant 1, the cosine function is positive. From 3 pi over 2 to 2 pi, we are in quadrant 4. And for the cosine function, that's where the cosine values are positive. So quadrant 1 and quadrant 4, the cosine is positive. We know that from our work with the unit circle. From pi over 2 all the way to 3 pi over 2, well, that takes us quadrant 2 and quadrant 3. And that's the left side of that unit circle, and that's where the cosine is negative. So again, not something that you have to memorize, but something that hopefully makes the connection between the unit circle and the graph of the sine and cosine function. So we'll take that picture that I just drew. We can see this is one period of the function. How do I know that it's one period? Because I started at 0, 1, and I'm ending also at 1. So I should be able to, I could stamp this and pick it up and move it to the left and move it to the right. And I'm going to get a picture that looks like this. And very similar characteristics, I would say. The domain of this cosine function is also going to be from negative infinity to positive infinity. Even though we only see it from negative 4 pi to positive 4 pi, we know that we could just keep on adding to that to the left and the right. And then the range of the cosine function, we're not seeing anything smaller than -1. We're not seeing anything larger than 1. And of course, it's including those values, and that's why we have the closed brackets.